G'day, it's Richard Mohan from Mars Classes again. In this episode we're going to have a look at the relativistic addition of velocities. In traditional addition of velocities, I think most of us are quite comfortable with adding or subtracting velocities. But when it comes to relativistic, sometimes it's difficult to determine which is u dash and so on when we're applying a formula. So historically you've done things like if there's a kid on the back of a truck, she throws an apple and the truck's moving forward at 20 metres per second, she throws the apple backwards at 5 metres per second. Relative to you on the ground, what is the velocity of the apple? What you do is you just add the velocities head to tail and you get a net overall velocity of 15 metres per second. You're pretty comfortable with that. And most of you have probably seen this equation here that you use when you determine the actual velocity when you're doing it. Addition of velocities at speeds approaching the speed of light. But application of that equation causes some concerns because you don't know what is u, you don't know what is u dash, you don't know what is v, and you get a bit confused. So I've come up with a method which seems to work and most students seem to be able to handle it. Imagine this situation. You've got a square guy and he's seeing a round guy passing by in a rocket that's moving relative to him at 0.6 times the speed of light. And the round guy in the rocket sees a ball moving within that rocket toward him at 0.4 times the speed of light. So to do this type of a question, you draw a diagram with all the moving objects in it. So you've got a square guy, you've got a round guy in the rocket, and you've got a ball. Next, you draw arrows to show what object or objects each observer is observing. Now we know the square guy is seeing both the round guy moving and the ball moving. The round guy is just looking at the ball moving. So we've got 3 arrows there. The third step is you determine which is u dash or v using these rules. U and v are velocities measured by the same observer for different objects. So the square guy is seeing both the ball and the round guy. And u dash are velocities for the same object measured by different observers. Now, the same object that both these observers are observing is the ball. So u dash are the speeds observed by each of the guys on the ball, and v is the velocity that the square guy observes the round guy moving at. Now once you've got them, it's simply a case of applying those values into the equation. Now if we stick them into the equation, we will find out the value that the speed the square guy sees the ball travelling at. When we plug them in, we get those values going in there. Now you'll notice too that I've got 0.4c is now negative. That's because it's travelling back toward the round guy, and so that direction really matters, as it did with the girl on the truck. The apple was going backwards compared to the velocity of the truck. Okay, so let's have a look at an example where we're adding these velocities at relativistic speeds. We're looking at a spacecraft coming toward the Earth, firing a missile at the Earth. Now, if that is the situation we're looking at, we've got a few things to look at. We've got the spacecraft coming toward the Earth. It's approaching at a velocity of 0.7c. If we're looking at the missile, now the missile is observed by both the Earth observer and the observers on the spacecraft. So that's going to be a u and a u dash. And if we're questioned what is the speed of the missile as observed from Earth, we can put in a few values into an equation. So one way of looking at it is u is the velocity of the object in the stationary frame, which is the Earth. U dash is the velocity of the object in the moving frame, which is the spacecraft. And v is the relative velocity of the moving frame to the stationary frame. So if I provide some values, if that v value is 0.7c, and the u dash value, that is the velocity of the missile relative to the spacecraft, is 0.5c going away from it, what will be the speed of the missile as observed from Earth? That's what we've got to find out. If we plug those values into the equation that we have, we put them in and we'll come down to this value here, 0.89c. Now does that make sense? If the spacecraft is travelling toward the Earth at 0.7c, and if the missile is going away from it, toward the Earth, it has to be relative to the Earth travelling greater than 0.7c, but it can't ever be more than c. Nothing travels faster than the speed of light. So 0.89c makes sense. You should always be asking that question once you do these calculations, does it make sense? And in this case, yes, it does make sense. Let's have a look at another situation here. This time the spacecraft is being a bit gutless. He's running away from the Earth and firing the missile back toward the Earth. So he's still got a relative velocity, this time away from the Earth, of 0.7 c. This time he's firing the missile relative to the spacecraft at 0.5 c toward the Earth. That's in the opposite direction. What will be the speed of the missile that the Earth would observe? Now, when we assign the values, it's still the same u dash and v. It's just that now we've got the spacecraft is going away from the Earth. When we apply those u dash and v to the equation, we see that the v is negative 0.7 c because the spacecraft is going away from the Earth. So when we plug those values in and we come down to our final value at the end, we get a value of negative 0.308 c for the relative velocity of the missile relative to the Earth. Does it make sense? Yeah, it does. The spacecraft's going away at 0.7 c and it's only firing the missile back at 0.5 c relative to itself. It's not going to be approaching the Earth. The missile is still going to be going away from the Earth. And is it going to be travelling at 0.7 c away from the Earth? No, it's not, because that's the spacecraft velocity. It's going to be going a little bit less than 0.7 c, well, quite a bit less than 0.7 c away from the Earth. So again, you always say, does this thing make sense? Now you can do this calculation another way using a variation of that equation, and if you plug those values in, you're going to get the same answer when you do it. But this time you get it to negative 0.308 c again. It's a little bit longer to do. So sometimes picking one version of the equation is quicker than the other. Okay, if you found this of any use, please subscribe to my channel and give it a like, and I'll see you next time.